the firm Sizemore and Associates. Sizemore and Associates is a firm of architects and engineers that specializes in energy consulting. They consult other architects on the design of new structures, and they also work extensively on retrofitting existing buildings. Mr. Haley received an engineering degree at Columbia University. He studied at Pratt and received his architectural degree from that school. And he spent 8 years in Alaska in private practice. While he was there, he took courses in Arctic studies at the University of Alaska. He has a very broad background. He's lectured extensively across the entire country. In the last month or so, he has presented over 30 lectures, in the last 12 months or so. He's presented about 30 lectures on the topic. So we're very fortunate to have with us today Mr. Jack Haley.
Thank you, Bob. It's a real pleasure to be here, looking at all your bare branches and your dismal, rainy weather. You get kind of sick of azaleas and dogwood and all that kind of stuff this time of the year. That's why I like to get around. And to really make this the full impact of this climatological change, I left Atlanta Sunday night and went to Mobile, Alabama, and then came directly here from Mobile yesterday. So nice weather you're having. As Mr. Sorrell said, to put it in a little different perspective, we're getting very far up the creek and our paddle is getting a lot shorter. And there's a heck of a lot we have to do. And we can't do it all in the design of new buildings. A number of people have made estimates that say to us that by the year 2000, when the energy crunch is right here in our laps, and we've lost that paddle, 80% of the buildings which will be existing and using energy at that time are built today. And our building inventory between now and the year 2000 will only increase about 20%. So the place where we have to really start, architects, engineers, building owners, everybody, is in a tremendous program of conservation among these buildings that we have, right from the single-family house to large multi-storied buildings. This is what we have been doing. As a matter of fact, Sizemore and Associates have been in existence as architects and energy planners for going on 4 years now. And as an active architectural firm with 10 people, we've designed 2 new buildings in 4 years. All our work has been in redesign, such as the headquarters building of the American Institute of Architects in Washington. That was a 4-year-old building, cost about $7 million, and you architects will know the squabbles that went on while the board of directors was selecting an architect. However, they got an excellent building by contemporary standards, and yet the Institute decided in 1976 to use their own building as a case study to see what could be done in reducing energy consumption in a good building. And as energy consumption figures go on BTUs per square foot a year in Washington, the AIA headquarters building is an excellent building. Well then, fortunately for us, they selected us to do the job. We feel very proud about that. We're the only architectural firm in the country that has 25,000 contemporaries as a client. And believe me, if ever you architects have designed churches and worked with church building committees, try working for the board of directors of AIA. That is really something. Anyway, we're just about finished with the project. We're in the construction stage, construction modifications to the building, and that's finished, and then we'll have a year of monitoring. But right now, it looks like we have reduced energy consumption in that building by 50%, at a total cost, including our fee, of about $200,000, which AIA will get back in a little over 2 years. We haven't done anything very drastic. And the further we go, the more we find that drastic measures are not really terribly necessary. Probably the most drastic thing that I've done is get the head of maintenance of a university fired, but it worked. We reduced energy consumption on that entire campus by 30%, and it's strictly an operational procedure. I firmly believe that every dollar of energy that we consume in the built environment in this country, of every dollar, we just purely waste at least 50 cents worth. And it's not bad building design, and it's not cheap mechanical systems or anything like that. It's people. And so we have evolved the philosophy. Is this thing humming? I'll pull it down a bit. Out of these observations, we have finally decided, and probably a lot of you have thought about this, but buildings don't consume energy. A building is an inanimate conglomeration of materials, and if you don't use it, it's not going to use energy. It's the people in the building who use the energy. And the way they use it is very, very important as to the amount of energy that the building is used. I could tell you more war stories and horror stories about some of the things we found. I'll tell you one, and it'll lead you to understand why this chief of maintenance at Oglethorpe University worked someplace else. We were doing a comprehensive campus energy management plan, and one of our mechanical engineers and I walked into the basement of the student union one day, and down there was a 2,000-gallon hot water tank, gas-fired generator that was making 160-degree water for the kitchen, cafeteria, and a few washrooms in the building. Well, here's this big 2,000-gallon horizontal tank, heavily insulated, and above that's an expansion tank, and on top of the expansion tank is a pressure relief valve. And apparently the seal had gone in the pressure relief valve. Now that valve probably, in a hardware plumbing supply store, would cost about $15, and you'd have to shut down the hot water system, let it cool down a little bit, unsweat the fitting, and resolder it, and you're back in business. Well, I'll never say who did it, I just took a picture of it, but somebody found about a 6-foot length of gutter, you know, like you hang on the eave of your house, and carefully notched the end of it so it would fit around the stem of the valve, and then hung it from the ceiling with wire so the water would be diverted down onto the floor and into the floor drain, and it wouldn't hurt the insulation on the storage tank. That must have taken a bit of time and ingenuity to do. We measured the flow on it. It was 4 gallons a minute. It worked out to $98 a month for heating that water that was going down the drain. So that was the end of that guy. But we've found so many things like that that it's absolutely ridiculous. And also in just plain operations. We worked with a school district in right next door to Atlanta in DeKalb County, and several years ago they wanted to do something about energy conservation, and we made them a proposal that we would go into their schools and study them and everything like that, and I guess we cost too much because it all boiled down to a couple of hours of consultation. And then they appointed a committee, or the superintendent of schools appointed a committee of the business manager and assistant superintendents and some principals and so forth. And with our help, they printed a 20-page guidelines for the operations of those schools. When they open in the morning, when they shut at night, when the heat is turned on, when it's turned off, what the maximum temperature is in the wintertime, what the minimum temperature is in the summer and on the air conditioning period, established light levels, restructured their school bus transportation system, and without spending a penny other than duplicating this guidelines and having a little cover made, and that whole thing probably cost $100. They have managed to cut their energy consumption by 28% across the board, and that's in 124 schools. And they haven't done anything yet. All they've done is tighten up the ship. Now they could go back and start making good modifications, mechanical modifications and so forth, and probably cut it another 28%. And so when we say, and we can back this up, that we can design a new building to be 100% more energy efficient than most of our contemporaries, that doesn't mean an awful lot. 100% more efficient means 50% less energy. And yet you can do that in any building. It's not a big deal at all. We found that in commercial buildings, we'll tell the owner or the manager of the building that if he'll let us talk to his operating engineer for a few minutes, this is when we're sort of making a proposal, you know, and fishing for a job, just let us talk to your operating engineer and we'll tell him what we're going to do. And a month from now, check your bill, and with adjustments for weather, you'll probably find your consumption down about 10%. And so we get with the operating guy and we tell him that we're going to do things like check filters, check time clocks, check fan belts, check bearings and all this. And then we leave. And then this guy suddenly realizes that this is what he's being paid to do, but he doesn't get around to doing it because Mr. So-and-so's secretary has a coffee pot that doesn't work, and he's going to fix that. And then I know in our building, I can get our maintenance man any time to tune my car or change tires or simonize or anything. Yeah, he has all that kind of time. Well, when the guy realizes that we're going to sort of pick him apart, he goes and he changes filters, and he tightens drive belts, and he lubricates bearings, and he checks his time clocks, and he checks his thermostats and all. And by God, immediately there's about a 10% reduction in energy consumption in that building. It's that simple. Anyway, let's get on a little deeper into some of the things you can do to really impact on an existing building. We find, generally speaking, that most buildings, I don't care whether they're schools or hospitals or office buildings, are at least 100% overlighted. And there's generally a good reason for that lighting. We architects over the past 30 years have become slaves to glass buildings or curtain walls and so forth. I made a remark up in New York before a group of architects, the reason that New York has so many curtain wall buildings is that there weren't enough architects and designers left who knew how to detail a good masonry building anymore, or a stone building. And I reminded them of a cartoon in the New Yorker back in the 60s. It was an architect's office, and there was a roll of paper on the wall like butcher paper. But it had a grid printed on it, and this guy was standing there with his scissors and saying, how tall is this building going to be? And he was going to cut an elevation right off the roll. But we did become enslaved with it, and we developed terrible glare problems. So then, after making this all-glass building, we put in Venetian blinds and drapes, and then we had to turn the lights on. And it was nighttime in that building all day long. There never was daylight. You couldn't stand it. There was just too much daylight. Well, we found that the use of either reflective or glare-reducing films applied to the glass are very effective. At the American Institute of Architects building, we have put, it's called Solar Guard. It's not reflective, it's just a glare-reducing film that's applied to the inside of the glass, which reduces glare by about 70%. And if we reduce glare by 70%, we can reduce artificial lighting by 70%. And if we reduce the lighting by 70%, we're cutting a tremendous piece out of the cooling load, and so we can cut our air conditioning way down. And this was the big magic thing that we did at the AIA headquarters. We have 2 absorption chillers there. One of them is now on standby for the life of the building. It'll just wait there until the first one that's running breaks down, or they change over for overhaul or something like that. But we've cut the load tremendously just by reducing glare, because you know why we need light. Talk about glare. All we need is good contrast between black and white. Colors vary, of course, but for most of our purposes, what we need is a good black and white contrast. And we can do that down to minimal light levels if we don't have this glare to combat. I was talking last week to a group of school administrators in Orlando, Florida, and we got on the subject of light levels in, gee, that's nice. We got on the subject of light levels in classrooms. We were in a conference room in a hotel. You've all been in them, you know how they are. And I remarked, I really thought it was great. There were about 40 people in this room. We had fluorescent lights in the ceiling. And the whole side wall was glass, looked out on the swimming pool and palm trees and so forth. And they had blinds drawn. And I said, well, why do we do this? Why don't we raise these blinds and turn the lights out, you know? And, oh, we won't be able to see. So the lights were on a dimmer, and I adjusted those, and I raised the blinds. I said, how's this? Is it all right? Oh, yeah, fine. They're all taking notes and so forth. I said, take a guess at the light level. Well, it started at 100 foot candles. But they knew that that wasn't quite right because, you know, I wouldn't be proud about 100 foot candles under those conditions. And they started coming down and down and down, all guesswork all the way. And I took out a GE light meter and put it on the table. And I said, look. And they were all very comfortable, working, taking notes and all, at 22 foot candles. But we had no glare. And it was absolutely fine. You can do that. And get one of those, practitioners. It costs $35, made by GE. And they really surprise you. So that's an awful good place to start in redesign. Start with the lighting. Also, we find that in most redesign projects, we improve the comfort level of the building. And people enjoy it more after we've finished. One of the things that we don't look at, engineers don't look at, In fresh air supply in a building, we have certain standards that we have to follow, and so many air changes an hour and so forth. And we size ducts according to some archaic rules that I don't know where they came from. But we don't do anything about air velocity. Now, with a given CFM in a low velocity, we'll be much more comfortable at a lower temperature than we will with the same CFM at a higher velocity. I learned things by trial and error and so forth. I was winter before last at the up at the University of Kentucky, and I was staying in the Hyatt Regency in Lexington. It was pretty cold out, and I got back to my room that night, and I was going to watch TV, and I turned the heating up, and the fan came on, and I was sitting, the grill was over the bed, and I was sitting out like at the foot of the bed in an armchair watching TV. And here was this blast of air hitting me from my grill. And I was cold. And I looked at the thermostat, and it was set on 70. And I turned it up to 75, and I was still cold. Finally, I got it up to 80, and I started to be comfortable. And of course, as soon as I got out of that air blast, I was hot. But if that register had been, say, twice as big as it was, I would have been getting the same number of CFM, and I would have been completely comfortable at 70. It's the same, you know, you go out on a summer's day on this side of the building, and it's probably 80, and you're hot, and you walk around the corner of the building, and there's about a 5-mile-an-hour breeze blowing, and you start to be comfortable. Well, just the reverse is true in heating with forced air systems. If the velocity is too high, you have to raise the temperature. And we've found this out, and people say, gee, it's so much more comfortable. Okay, comfortable? Well, let's go back to 68 instead of 72. And it works. In another good area to look for great energy losses when you're retrofitting buildings is look at the roof. Most buildings that have been built in the last 20 years have a minimal amount of roof insulation to begin with. And then a lot of funny things happen to the roofs. You architects here will know that we write very, very careful specifications for roofing a building. And we're generally using rigid insulation of one sort or another. And we say that the roofer shall put down no more insulation on the substrate than can be covered and mopped in with roofing material by the end of the day, because we want to keep that rigid insulation dry, because wet insulation is no insulation at all. We don't say a darn thing in the spec about the fact that the insulation with the paper wrappings torn and everything has been sitting in a building material supply yard for maybe 6 months, and the roofer brings it out to the job and puts it on the ground on a couple of 2x4s and puts a tarp over it, and then we have 2 weeks of rain, and probably when the insulation goes on the roof, it's too wet to meet our standards anyway, but we've never said anything about that. And we had a situation like that about 5 years ago where a roofer did exactly that, put the rigid insulation down, very carefully covered it and all, and it was done in the winter time, but dry weather. And in June, the blisters started forming all over the roof. And it was just the hot June sun hitting that roof and actually boiling all the moisture that was contained in that rigid insulation and just blowing blisters all over the roof. What are you going to do about it? You know, a new building? Does it need a new roof already? It's an embarrassing situation for an architect to get into, believe me, when you look at a $40,000 roof on a building. There are a number of items in here that I'd like to touch on. Material that Bob sent me. A lot of good thinking here, Bob. Minimal exterior glazing. No, I don't agree with that. I say maximum. Effectively placed. Let the sun in. Let the sun in when you can use it, keep it out when you can't use it. And the best way that I know of is lots of glass on the south side of a building for low winter solar penetration, and properly placed sunshades to keep the summer sun off the glass. It works. Works very well. I'm just going to look at some of these things and comment on them. Yeah, variable air volume. That's just what I've just been talking about. Alternate fuel, an immediate solution. However, the only ones available are electric and oil. I would never recommend to a client in the construction or the design of a new building now that you look at anything but all electric for your building. And the reason I say this is that I don't know, and I don't think John Purcell knows, and I don't think Mr. Sorrell knows, how we're going to generate electricity in the future. But we are. It may be all nuclear, it may be coal, it may be gasified coal, maybe wind generation, maybe photovoltaics, but electricity is the one thing that we're not going to do without. I can see not too many years ahead when there just won't be any more natural gas. Not because there isn't gas, and this is something that disturbs me. The petroleum geologists, you know, say, oh, there's just an unlimited supply of gas and petroleum right here in this country, and all you have to do is deregulate prices, let them seek their own level, and we'll get the gas and oil to you. I was talking 2 weeks ago in Louisiana to a man who's in the business of drilling gas wells, and he said, yeah. He said 10 years ago we could punch down a gas well anywhere in the state of Louisiana for about $150,000 and produce gas. And we know there's a lot of gas here. But he says right now it costs over $1 million to put down the same well. And they have to keep going deeper and deeper and deeper. And so that gas is down there, oil is there. I don't think it will ever be economically feasible to extract a great deal of it. We just won't be able to afford it. So that, to you designers, I would say, don't rely on any other source, major source of heating and cooling a building from now on out but electricity. Because one way or the other, we're going to have it. I don't think the way we distribute electricity is very economical right now. Our losses are terrible. We get about 30% of what's produced. But I like to look ahead to the photovoltaics. And I can see, as John said, you're hoping for what, $200? $250 a kilowatt. Well, in my study at home, I have 2 solid-state transistor radios. And one is about this big that I bought in 1962 for $150. It's a Sony. And right next to it, I have a Sony that I bought last year for $5. And they're both, you know, exactly the same. They'll bring in just as many stations, have as equal volume and everything like that. But the cost of transistors has gone down in the last 15, 16 years, something like 2,000%. And I can see that happening to photovoltaics if, I think it's going to need a shove, like solar is getting now, demonstration projects and so forth, to bring the cost down. Because wouldn't it be a lot simpler than, John showed you the big wind generators and the big solar boilers. Then you've got that transmission and all that light loss and all that conversion, and you have these tremendous losses. Wouldn't it be better if every one of us had an array of solar cells on our house to do the same job? We wouldn't have any line losses. We could have an array of cells and some storage batteries. They have to be improved. And all day long, if we're not using electricity in the house, our voltaic cells can be charging batteries. Then we can draw on that at night. I'm building a new house, and I'm doing a lot of silly things with it. One of them is I'm putting a photovoltaic-operated attic fan in the house. I don't know how effective it is. It's supposed to be 150 or 200 CFM, and it sells for $365. But I'm putting it there because the word has gotten out that this house of mine is 100% solar, and that's the only thing I'll be able to show people is that little panel of photovoltaic cells on the roof that's running the fan. Because my house is solar, and it started out as a solar house, and I spent 6 months on designing it. I started with a whole roof of collectors, 300 square feet of collectors. And I had a big storage tank under my greenhouse, which is attached to the house. And I thought, this is great. The heat losses from the storage tank will keep the temperature up in the greenhouse. And then my wife and I like swimming pools, and every place we've lived we had a pool, so we put a swimming pool in. And I thought, that's a good idea, because in the summertime, when I'm not using my big 300 square foot solar system for heating, I've got to do something sort of to protect the collectors. They're not going to do a great job, maybe a little assist with the pool, but if I circulate pool water through the collectors, they'll protect the collectors from high stagnation temperatures and maybe raise the pool temperature a few degrees. Well, I had the classic system all designed with the 300 square feet of collectors and a water source heat pump with a hydronic coil built into the duct. And mode 1 would be when I need heat in the house and I'm collecting heat from the sun, then I would circulate through this coil and into storage. Now, when the house no longer calls for heat, but I'm still generating heat with my collectors, then a three-way valve would bypass that coil, and I'd go direct to storage. Then my next phase would be from my storage through the coil, and then when the temperature in the storage tank got below about 90, my heat pump would take over and use the 85 to 90 degree water in the storage tank. And here was my swimming pool just sitting out there doing nothing. And I started putting things together, and I thought, golly, this greenhouse of mine that I was going to put the storage tank under, in Atlanta on any clear day in the wintertime, the average December day, it will collect 300,000 BTUs. And with a reasonable amount of mass in the floor and the low walls of the greenhouse, I'll hold enough to carry me about 30 hours. And I can just pump that through a couple of ducts into the rest of the house. Then I got talking to a friend of mine, has a swimming pool, and he bought one of these solar blankets for his swimming pool because he likes to swim all year round, and it was costing him too much for gas to heat the pool. He had a gas heater. I used to have one in my old pool too. 180,000 BTUs, boy, they really eat the gas. So I bought this solar blanket, which is nothing but a plastic, looks like a waffle. You've probably seen it. They use it for wrapping machinery when they ship it and like that, you know. And he bought this and floated it on the pool and found that all last winter, the sun was able to keep the temperature of the pool up between 65 and 70. And so I thought, that sounds good. So I took off some more collectors. Now, the way the house will be finished next month, I have the 2.5-ton heat pump just connected to the swimming pool. And the solar blanket, maintaining 65 or 70 degree temperature throughout the winter, will be ample for my heat pump to draw on for my heating. Besides my greenhouse, which is going to be supplying a lot of heat also. Then in the summertime, the swimming pool becomes the heat sink for my heat pump when it's in the cooling cycle. And we'll also warm up the pool. If it gets too hot, I'll make a fountain. I'll aerate it to cool it. But you know, you start going into these things and you start throwing away hardware. And now I'm down to 3 Woollen solar bond collectors built on the roof into a 2x4 frame and some corrugated Phylon for cover. I'm tying that to a 50-gallon hot water heater, and there's my solar hot water heating system. And boy, the cost of my solar system has really come down. And as my builder says, he's from Georgia, I'm not. He says, you son of a gun, you're getting that pool free. Because he told me that, well, the swimming pool is costing about $3,000 and the heat pump's about $600. And he says that's just about the cost of an HVAC system for a house the size of mine. Another thing I did, the house is slab on grade, and instead of running all my ducts overhead from my little mechanical room where the heat pump is, and then having to insulate the ducts, and then even that, having duct loss, I cast 6-inch stovepipe into the slab and got a couple of inches of concrete all around it, so when the stovepipe rusts out, I'll still have some concrete tubes. So I have no duct loss, because losses that ordinarily would be in the attic are now in the floor, which helps heat the house. And by our best calculations, this house is going to cost, this is just for heating and cooling, probably $35 or $40 a month to run. And it's all electric, too. I mean, when I say all electric, there's the heat pump and its little blower and a quarter-horse circulating pump between the swimming pool and the heat pump. After we got all that worked out and started building it, the state of Georgia came to us to design a residential complex on Ossabaw Island. Ossabaw Island is an interesting place. It's 35,000 acres, one of Georgia's Golden Isles. I don't know whether any of you have ever been down there. It's quite a beautiful place. Sea Island, Cumberland, Ossabaw, Sapelo. Unlike most states, most coastal states, Georgia has, over the past 6 or 7 years, progressively acquired all these islands. So they're not resort areas like Miami Beach or anything like that. Ossabaw will be a 35,000 acre wildlife preserve, and consequently they will need residences and a shop and office building like that for wildlife biologists, research people, and so forth. And so, knowing what we were doing with solar, the State Energy Office recommended us to the Department of Natural Resources to design these buildings, which had to be solar, because the alternative is #2 fuel oil, which has to be hauled out to the island on a barge in 55-gallon drums, and because of tides and all that kind of stuff, by the time it's landed on the island, it costs about 75 cents a gallon. And it's just out of the question to use that for heating. And even we are putting a generator on the island while we look into a wind generator, but that's only for lighting and for refrigeration. Well, our first estimate for the solar systems for these houses was, considering the location and all, about $7,000 a house. And then we got looking at it from the standpoint that we started looking at my house 6 months ago. And we have now wound up with these houses. They're a living dining room, kitchen, 3 bedrooms and 2 baths, about 1,600 square feet, I guess. They're completely passive for heating and cooling. Greenhouses, again, on the south side for heating, and then by proper placement of windows, oriented to the prevailing breezes, and low windows on one side and high windows on the other side, and vaulted ceilings throughout so we can get proper airflows. That'll keep the places cool. The backup heating system, and the state, you know, DOE says it, HUD says it, the states all say it, you got to have 100% backup with a solar system. It's a wood stove. And the people are going to be out there, the biologists and so forth, they're all nature people, and they say, oh, that's fine, we love that. So there's the backup on this, the wood stove. And so we do have solar houses, and everybody, including the governor, are fascinated by them. But there's no plumbing. There's no hardware there, see. And this upsets people, and I'll tell you a funny story in relation to that. I heard this about third hand. A lady architect out in Albuquerque designed a 100% passive solar house. And she got a lot of publicity in the papers, and people started coming out to look at her passive house. I've seen pictures of it. It's heavy adobe and a lot of glass on the front and overhangs for shading and everything like that. You know, the same way that Pueblo Indians did it a couple thousand years ago. She's reinventing an old wheel. But people came out and they kept saying, well, where's the solar? Where's the solar? What makes it work? What makes it go? And she got so teed off at all these questions that she went to an automobile junkyard and she bought things like a tachometer, a speedometer, an ammeter, some red lights, and she made up a panel which she has in her kitchen. And when people come to see her solar house, she plugs this in, you know, and the tachometer is reading about 3,400 RPM, and the speedometer is saying something else, and this light's flashing, you know, and this needle's going like this. And she says, there it is, there's the brains of the whole thing. She says, that's what makes it all go, and people are real happy and satisfied, and they walk away. Let's talk a little bit about savings through design in new buildings. I think orientation is number one. And proper orientation of a building along with its design can reduce its energy consumption up to 20%. Oh, this is a battle that I have all the time, not with clients, but with other architects. They hire us to help them design a super energy efficient building. And then the battle is, but the good view is on the north side, see? And that's the way we want to face the building, because of the view. And so we have to take another approach there, and maybe we sacrifice some view to get the building oriented properly to the south if we're going to use passive solar, and oriented properly for breezes and so forth. Another area where there's a good opportunity for savings is what we call conditioned outdoor spaces. And not only, you know, covered walkways, and of course people have been doing that with campus type schools for years and all, but work on them, get planting in there, get your landscape architect working with you right at the beginning, so that these spaces are truly conditioned. You can get, gee, I wish I had a blackboard. Oh well. You can get some good results by creating almost wind tunnels. In other words, you have a fairly large opening on the side of your building where the prevailing wind is, say, during the warm weather. And you progressively reduce the size of that. Maybe this opening comes into a corridor, and you reduce the size. Daylighting. Golly, you know, we forget about daylighting. We don't pay any attention to it. And the interesting thing is that in England and in Europe, generally speaking, that is the first consideration in the development of the design of a building. They even go so far as to build like, quarter-scale mock-ups of buildings or parts of buildings to study daylighting. There's a tremendous opportunity there. We developed, not because we're extra smart, but because we just figured some things out. We developed an eyebrow, which is just an arc, a plain arc of a circle, and setting that maybe 8 feet above the floor in a building with or a room with a 10 or 12 foot ceiling, and adjusting that properly, we can bounce daylight back 30 feet into the building. And then in the summertime, it's also shading the glass that's underneath it from high summer sun. And with louvers or what have you, you can adjust that. But you don't have to have a reflective surface. A white surface will do. You don't bounce too much heat in. It works. We worked with another architect on a big office building where we were able to cut that's 400,000 square foot office building. Worked out in tiers and so forth, so that where we could use daylighting in 60% of the building 95% of the time, during the normal working hours of 8 in the morning till 5 in the evening. It's worth looking at. I mean, taking a long look at it. We're working now on a project for Shell Oil in Houston, where we're using daylighting to the greatest extent possible. Shell has gotten so enthusiastic with the idea that they're willing to finance the construction, if you believe it, of a full-scale mock-up of a section of one of these buildings. It's an office park for Shell Oil and a series of buildings. And this mock-up will be 2 stories high and about 30 by 60 feet. And this is just the mock-up to work out the bugs on the natural daylighting. But they're really enthusiastic about it. So, and of course, you know, lights use electricity and lights generate heat and use more electricity. And so if you can get down there and really work on this, you can save a bundle. And you not only save, you see, it doesn't cost any more to build an energy efficient building than it does to build an energy dog. It can cost less. These reflectors that we talk about, they're not expensive. Everything else is about the same. But by doing this and making your shell of your building work for passive heating, for natural daylighting, for all these things, then you start cutting down on the mechanical equipment. And so if you do have to spend an extra $2 or $3 a square foot in the shell, then you can probably cut your mechanical and electrical down and get that money back and really make some money on it. You know, in the past 40 years, the cost of MEP in a new building has gone from 8% of the construction cost, and this was 1946, 47. The average was 8% of the total construction cost, to 35 to 38% now. And I blame us architects. I don't blame the engineers. We've given them a bunch of tents to heat and cool, and we've forgotten all about this stuff, and they've met our demands. We just give them anything, glass boxes, say, here, heat it and cool it, and they do. I compliment the engineers, they're good. All it takes is money, and they get it. So, yeah, passive solar heating, back again to my swimming pool and my heat pump. In larger buildings, tremendous opportunity for passive solar heating. I'm going to tell a story now about some of these pictures that John showed us this morning. That Towns Elementary School, and this is sort of a retrofit thing too. What's the cost of that? $750,000, wasn't it? The solar system, I think it was. $750,000 for a solar heating and cooling system on that school. A couple of years ago, we had a training seminar for architects and engineers in Atlanta, teaching them our techniques of measuring losses in buildings and finding things to do. And so the chief architect of the Atlanta school system gave us a set of drawings of the Towns Elementary School before the solar system was put on it. And we gave it to our students and said, here, just figure out, see what you can do to increase the energy efficiency of this building. And at the end of the second day, they came up with an answer that if somebody had spent $25,000 or $30,000 on that building, they could have cut that solar system cost in half. So it's you know, one of these things. The yeah, passive solar in large buildings, it's great. Think of thermal capacity of your materials, like buildings like this. These are, you know, these are buildings that I say thermally are good. You have a lot of mass here. Heavier your building is, the better it's going to work. The people who sell metal buildings will give you all kinds of arguments on that, you know. They'll tell you that a 4-inch insulated metal panel has a U factor that's as good as 8 inches of concrete block faced with brick. And they're right, it does. The only thing is that the thermal capacity of that 4-inch panel is something under an hour, maybe 56 minutes or something like that, where the thermal capacity of the masonry wall with the same U factor is 6 or 8 hours. What does that mean? In a metal building with these good insulated panels, if you turn the heat off and it's 60, 70 inside and it's 20 outside, within an hour the temperatures will equalize on either side of that wall. With the masonry wall, it'll take 6 or 8 hours to do it. Well, there's a big opportunity for saving energy when you have massive construction like this. In the wintertime, you could probably turn the heat off in this building. If it runs until 5 o'clock in the afternoon, you could probably turn all the heat off at 1 o'clock in the afternoon. And the building would remain relatively comfortable till the end of its useful day. But in the lightweight building, you can't do it because it starts to cool down immediately. So use this and use the ability of the building to absorb the solar insulation that's available. There are all kinds of things, you know, trom walls, and you've all seen all this kind of stuff. Even people are experimenting with running piping through the south walls of masonry buildings, either for air or water transport. They work, but you gotta dig, and you gotta use your imagination in looking at them. Using the winds to cool. in the thought of orientation of the building, find out, you know, where your prevailing winds are. All this data is available. The National Climatological Atlas covers the whole country. You can really pinpoint it if you have a local weather bureau here or Indianapolis. Get their monthly weather reports. Climatological data will tell you every day of the year where the wind blew from, how hard it blew, what the temperatures were. But start to work with the weather. Learn about the weather. Learn the climatology of your area. And then start designing your buildings in that direction. Task-designed windows. Now, there are several ways to approach the use of windows in a building. And task designing the windows is a very important way to go. If the primary purpose of a window is to display goods and products inside the building, that's one thing. If its purpose is to let people see out, that's another thing. If its purpose is to let in daylight in sufficient quantity to keep your artificial lighting off, that's another thing. And then, of course, ventilation. You can do tremendous things ventilating a building with properly placed windows. You create air tunnels. If you have, say, large, maybe the prevailing winds in the summertime when you're in air conditioning, the prevailing winds are from the north. Well, now everybody will tell you that you shouldn't have windows on the north side of a building to save energy. But you can have them. And you have windows on the south side too, and get airflows going through the building. And if the windows on the north side are bigger than the windows on the south side, you'll increase the velocity of the airflow. They work. But it takes a lot of thinking, a lot of planning to do this kind of stuff. We say keep the sun out in the warm weather and let it in cold weather. Bury parts of the building. A firm in Northbrook, Illinois, came to us 6 or 8 months ago. They were commissioned to design a library, a public library for Zion, Illinois, which is on the west shore of Lake Michigan. The library board and the county board of supervisors had told them that they wanted a solar building, by golly. That's the way they were going to do it. They wanted a solar building. So this firm came to us, and the first thing we did, as we always do, is dig out our climatological data and look at that area. And we found that in December and January on the west shore of Lake Michigan, you can have as much as 30 days, continuous days of cloudy weather. Now, how in the name of everything that's holy do you make a solar building when you have nothing but cloudy weather when you need solar heat? And so we kicked it around in our office and went back to them with a suggestion that let's do a couple of things. Any objection to burying the building in the ground? And no, they didn't have any objections to that. How about passive solar and artificial lighting? Well, that looked fine too. Well, we wound up with a 27,000 square foot building whose main floor is 10 feet below grade. And then there's a sawtooth roof with a series of glass clear stories across the roof, which are set so that natural daylighting can be used, 75% of the time. The low winter sun will come in and help heat the building. And there are projections to prevent overheating in the summertime. And when we got all done and figured all our load calculations on it, we found that this 27,000 square foot building had a peak heating demand in the wintertime of 30,000 BTUs an hour, which is about the equivalent of a 3,000 square foot house, probably, normal house. And so what's left for heating and cooling is a very, very small thing. Everybody's quite happy and excited about the thing, but it's a new concept. Initially, they wanted, collectors on the roof, and we don't have any collectors. using the mass of the building. For instance, the south end of the building is all glass, and there's like a little amphitheater so that we could expose this glass to the sun. Well, what do you think we did with all this glass wall? We came in about a foot on the inside and put book stacks all along there, because books are great for absorbing and holding heat, holding energy. They work well. Good storage. Another thing in design of new buildings is task lighting. This overall illumination, and I'm thinking mostly of commercial buildings now, just drives me crazy. And I think, how do we get into this? And then I remember, I've worked for a number of large firms and been in charge of production in most of them. And you architects know that in your firm or any other one you've worked with, there's always some nice kid who's struggling hard. He's not very bright, but you like him and you hope he'll improve. And so you always have to find a job for him. And in doing high-rise office buildings, the one thing we always needed was a stupid reflected ceiling plan. And, well, you know, anybody can draw a rectangular grid on paper, so I'd find this kid and I'd say, I need a reflected ceiling plan, typical floor. We're going to use a 2x4 lay-in ceiling and 2x4 lay-in fixtures, and I'd walk away. And he'd do a nice balanced drawing to please me, and he'd place the light fixtures so they created a pleasing pattern in the reflected ceiling plan. And I'd look at it and say, okay, and it would go on to the electrical engineer, and he'd say, okay, and he'd wire it up and circuit it. And generally, if it were a tight budget job and it was 5,000, 10,000 square feet, there may be one, there may be two switches to light the whole ceiling. And then we wind up with 120 foot candles in that thing. And nobody paid any attention to it. What I like now, like in our own office, we threw out half the light fixtures when we moved in, and we have task lighting if we use fluorescent, 2x4 fluorescent fixtures. Those are building standard, with the para-wedge lenses. Are you familiar with those? It's like a small egg crate, and they're silvered. And they shoot the light practically right down with just a little diffusion off to the side. If a person is right-handed, we set the fixture in the ceiling to his left. If he's left-handed, we set it to his right. Have flexible cable on them so we can move the things. We have, in our drafting room, the light level's about 40 foot candles, and everybody's completely happy with it. I have normally 20 in my office at my desktop. My partner does. The other architects who do mostly written stuff and calculations and all, we all like 20 foot candles very much. Go home completely relaxed at the end of the day. And, but every bit of lighting in that office is set up for a particular task. Our receptionist has lighting for what she does. Receptionist answering the telephone, doing typing and so forth. Everybody there has lighting designed for what they're doing. It's kind of hard to do in an open plan commercial office building, but it can be done. The only thing is the owner has to realize that if he changes tenants, he's probably going to have to change the lighting because the people are going to be doing different things. But it's all a matter of going through this whole design process with your foremost thought in mind that you're going to increase the energy consumption of that, energy efficiency of that building. You're going to make it the most efficient you can, and basically it's mass, it's orientation, it's using natural daylight, passive solar heating and cooling, if possible, and right down the line. If you just make a checklist and go off, you're going to wind up with a lot better buildings than we've all been doing for the last 25 or 30 years. Interestingly enough, we're going to wind up with buildings very similar to buildings that were built 50 and 60 and 75 years ago. They were energy efficient buildings. I think I've talked long enough. I'm about to lose my voice. Thanks for listening. Anybody have any particular questions at this time? Can you hear me? Yeah.
Do you have any particular ways of reducing the heat loss penetration when the sun is no longer beneficial? Or reducing the night heat loss?
Yeah. I think probably one of the most practical ways of handling that is with heavy drapes. There are all kinds of things. Have you ever seen the bead wall window? It doesn't work. They can't control the static electricity that builds up. And after they've filled it and dumped it and filled it and dumped it a half dozen times, then this styrofoam is stuck all over the glass. No, I think the simplest answer to that, of course, use insulating glass and then a good heavy drape with like a foam lining in it. You're not going to block it completely. Of course, you want to go a step further, you can have sliding insulated panels that close over windows. I think drapes, we've got to be practical about these things, you know. There are certain limits to beyond which it's just not worthwhile going. Any other? Yeah. Well, we didn't use it at all. We threw the whole active solar system out. And so we actually saved that money. Oh, I think, I think solar hardware is going to come down in price. It has come down in price quite a bit in the last couple of years. Isn't that right, Diane? Yeah. Well, thank you.
Thank you. I'll direct your attention to the sheet that you got early on called Agenda Subtopic Discussions. These groups will be meeting between now and 12 o'clock in various rooms in the buildings which are marked there. And this is your opportunity to ask some of the questions that are more specific to a specific area that you might have interest in. I will let you know that as out of each of those discussion sections, there will be a 5-minute presentation here at 12 when we're eating lunch to sort of let you know some of the things that were brought up and bring everybody up on the kinds of questions that are presented.